discussing questions. Right. So in our last class we have completed about isomerism. Now today what we will be doing is we will just work out some questions, okay, related to isomerism, and maybe 2 or 3 questions related to nomenclature and other questions. Okay. So from the next class we will go for the other theories. Whatever we have studied till now in the isomerism, just try to work out a few questions. Some of them are very easy and some of them are previous exam questions. Okay. You can just start writing the questions. First one, which of the below can exist as enantiomer? Which of the below can exist as enantiomer? You can note down the options. If you can get all these questions right, you have almost completed this isomerism. You can definitely answer any question. Which of the below can exist as enantiomer? Which can exist as enantiomer? It could be multiple answer also. Multiple options can also be there. D can exist as B or C. Why not A? We have discussed symmetrical. Okay, so it doesn't exist as enantiomer. Parallelly, you also draw these structures. A also, because it is very important molecule. Last class also we have discussed about it. These two are non-superimposable mirror images, therefore they are enantiomers. Okay? Enantiomers are not only in your organic chemistry. In organic chemistry also we say enantiomers are there, mirror images are there. Though the central atom is not a carbon, still we call it as asymmetric. We also get disymmetric. We say asymmetric. We also have a concept called as disymmetric. So whether the center is asymmetric or whether the center is disymmetric, they will be optically active. Asymmetric means C1. C1, in symmetry there are some point groups. Whatever molecule that is been given, you have to work out some symmetry elements. Based on those symmetry elements, we will derive a point group. Depending on the point group, I can say whether a molecule is optically active or inactive. So out of plenty of point groups, any molecule that belongs to C1 point group are called as asymmetric. Such a molecule will be asymmetric. Now there are some molecules where you have C2 or C3. This will have a C3 rotational axis. It will have a C3. Still it is optically active. So such molecules come under disymmetric molecules. This come under disymmetric, not asymmetric. You have to call it as disymmetric molecule because this has C3 rotational axis. A C3 will pass from here. No plane is present in it. Okay, therefore it is called as optically active molecule. Enantiomers exist for it. So along with C2, C3, C4 and so on, D2, D3, D4, D5 and so on, even they are found to be optically active. Okay, this concept is not there for you, but just remember 2 points. Any molecule that belongs to C1, Cn, Dn are optically active, right? So what is Cn? Only one rotational axis will be present. What is Dn? Dn means there will be one rotational axis plus what is the fold of this rotational axis? So many number of C2s will be there, which are perpendicular to Cn. Cn and C2s perpendicular to Cn. Okay. So any molecule that has only rotations, all such molecules are also optically active. Got it? So carbon asymmetry, you say no rotational axis, hence it is optically active. But even if rotational axes are present, such molecules are also optically active, provided Sn is absent. There should not be any Sn. Okay. So now coming to the conclusion, CON thrice, it can exist as enantiomers. Chromium glycine, glycinato. Finish this one. First one is okay. Second one, glycinato means N, NS2CS2, COO, but simply I am putting N and O because we are aware of the ligand, so simply I am putting the chelating rings. Does this has an enantiomer? Answer is yes, because it is a tris-chelated complex. You have an enantiomer. I have written only one of the geometrical isomers. There is also another geometrical isomer. This has its enantiomer. The another geometrical isomer is which one? We discussed all these things. These two are different molecule. I mean, these two are different isomers. This is called as facial. 3 nitrogens are related in a triangular manner. 3 oxygens are also related in a triangular manner. In this case, 3 nitrogens are related in a meridional plane. And 3 oxygens, they are also related in a meridional plane. So these two are different geometrical isomers. This can exist as enantiomer. This can also exist as enantiomer. Okay. So even this can exist as enantiomer. Suppose if the question is how many stereoisomers are present for this? Just let us extend the question. Let me extend the question. Cr glycinato 3 or triglycinato chromium. Triglycinato chromium. How many stereoisomers are there? Stereoisomers means geometrical isomers and optical isomers must be considered. How many geometrical isomers are there? 2. 2 geometrical isomers. One is facial, another one is meridional. 2 geometrical isomers of which each one can exist as optically active molecule. So this has its enantiomer, this has its enantiomer. I mean its mirror image is present, mirror image is present. So 2 plus 2, 4. How many stereoisomers? Altogether 4 stereoisomers. How many optical isomers? 4 optical isomers. How many geometrical isomers? 2. So number of geometrical isomers. How many optical isomers? How many optical isomer pairs? So what are the number of stereoisomers? 4. To get the number of stereoisomers, I asked you to add geometrical isomers and the optical isomer pairs. 2 plus 2 is 4. Right, so this is also existing as enantiomers. Third one, S. Remember, whenever you have 2 chelating rings and 2 other ligands are monodentate ligands, cis form will have its mirror image. Okay? Cis form will have its mirror image. Directly remember that logic. I am having dichelated complex. This one is cis chromium. Chromium En twice. Along with that you have 2 water molecules. Let it be 2 identical ligands or let it be 2 unidentical ligands. In this case it is identical ligands. There is no plane, remember. On board it looks like there is a plane, but there is no plane. This ring is above away, this ring is below towards you. So there is no plane in it, and hence it will be optically active. Cis form will be optically active. Therefore, you will find its mirror image also. There is a mirror image of it. So this will be one ethylene diamine, this will be another ethylene diamine. This is also optically active. Just asking for enantiomers is asking for optical activity. Fourth one, that is inactive because these are not chelating ligands. These are not chelating ligands. And a cis has been asked, so put 2 bromines cis to one another. The remaining 4 are amines. This is optically inactive because it has a C2 and 2 sigma B are also present in this. There is a C2 rotational axis and 2 planes are present in this. Since planes are present, you call it as optically inactive. Or else, I told you a simple logic. What is that logic? You have to write ligand pairs with trans. So one trans pair is NH3 bromine. Another trans pair is NH3 bromine. Third trans pair is NH3 to NH3. What was the logic we have discussed? Whenever you have 2 pairs of identical ligand pairs, amine, bromine, such a molecule will be optically inactive. Or at least if we have 1 pair of identical ligands, such a molecule will be optically inactive. You find both of them. You find a pair where there is an identical ligand. You find 2 pairs where there are identical ligands, amine, bromine. Hence it is optically inactive. So this is inactive, no enantiomer of it. Last one, 2 chelating rings. Previously I told you, it is just like this is one ligand, this is some other ligand. That is also optically active because it is a cis form. If you take a trans form of this, is it optically active? We are taking 2 ethylene diamines, amine and chlorine. Is it optically active? Means trans form will be inactive. The reason is this plane can be seen, exact plane you can very easily seen. Okay? So there is a plane in this, therefore it will become optically inactive. There is no enantiomer of it. One, 2, 3 and 5 have enantiomers. Fourth one do not contain. So you should be having some idea about symmetry also for this isomerism, that is at a higher level. And however the question might be asked, you will definitely answer it. Okay, take down the next question. An isomer of a complex, COEN taken twice, H2O, Cl2 and Br, on reaction with concentrated sulfuric acid, leads to loss of weight, Next, upon further reaction with silver nitrate, it gives white precipitate, which which is soluble in ammonia, which is soluble in ammonia, which is the complex, So you can just go through the question once. Answers will be simple, only thing is they just twist a little so that they can confuse you. Answers will be simple only. Option D. D, sure? Which one? C? D. Multiple options. You want multiple options? C and D. Okay, we'll go with D, majority. The question was about treatment with sulfuric acid. In the beginning of coordination chemistry, I have told you, suppose if you have a hydrate isomerism, how do you identify a hydrate isomerism? That hydrate isomerism you can easily identify by treating with sulfuric acid. Sulfuric acid is a dehydrating agent. Suppose if there is a water molecule which is outside the coordination sphere, such a water molecule will be taken away by sulfuric acid, the weight of the complex will drop. So whenever you have water molecule outside, only then sulfuric acid will be able to take it. If that water molecule is coordinating inside, sulfuric acid will not take that water molecule. So when I treated with sulfuric acid, weight of the complex has dropped. What is the meaning of it? Water molecule must be present outside the sphere, as simple as that. So this is one option. Second option. But the question went on to say that when silver nitrate is added, there is also a white precipitate. So when do you get a white precipitate? Along with water molecule outside, you should also have a chlorine. Maybe I may think that bromine is outside. There is a water molecule. Along with that water molecule, there could be bromine outside. Ionization isomers, that is also possible. But bromine will give you what precipitate? I mean what color? It will be yellowish, it will not be whitish. It will not be whitish. Second thing, whatever precipitate that is formed, it is dissolving in ammonia. So what is the meaning of it? It will form a coordinate complex. It will form a coordinate complex. Excess of ammonia will form a coordinate complex. So maybe at your MSc level or some other level, you might have precipitated it, but suddenly they will say to add dilute ammonia, 1:10 ammonia. You will say, why should I add dilute? I have concentrated, I'll add it. Suddenly it will be gone. So where did it go? It has formed a coordinate complex. Okay, that is your coordinate complex. So what is your option? D. D is right. This we have discussed in coordination chemistry beginning, where I have discussed about different isomers, hydrate, ionization isomerism. In that, if at all I put sulfuric acid, it can very easily take away water molecule present in the ionization sphere. You can just also write this. Silver chloride in the presence of excess ammonia will give you a coordinate complex. What is the name of the complex? Diamine silver 1 chloride. Diamine, double M. You have to put double M. Okay, next question. Now you have to think a little more, because what you have asked for multiple options, I am giving it here. COEN taken twice, amine, chlorine and sulfate. take some time, don't panic, just imagine that this is your exam. All the things we have discussed are coming here, nothing is from outside. Okay, here I'll write. A is enantiomers. Geometrical isomers. Ionization isomers. Linkage isomers. Enantiomers, geometrical isomers, ionization isomers and linkage isomers. CON taken twice, NH3Cl SO4, CONH3 taken 4, NO2 taken twice, NO3 taken twice, COEN PN NO2 taken twice, Cl, COGLY taken thrice. Now there are multiple options. You may get the answer, but just try to see that you take a little time, not a greater time, just try to take a little time and then try to answer it. Enantiomers means optical activity, that is the meaning of it. Simply remember, enantiomers means there should be some optical activity in it. Optical isomers must be present. Geometrical isomers, ionization and linkage isomers are known. So linkage isomer means you have to have an ambidentate ligand. There must be some ambidentate ligand to have a linkage isomer. That is the hint we have. Ionization isomer, there should be some ion in the ionization sphere. Here there is no ionization sphere. There is no ionization sphere means it does not have ionization isomer. Geometrical isomers, that depends. We have seen all different combinations for octahedra and square plane. Enantiomers, optical activity. Okay, let us start with the first one. COEN taken twice. Dichelated complex. So this dichelated complex can exist as cis as well as trans. Both cis and trans, but trans will be optically inactive. So it is existing in cis and trans. So first one, B is there. It can exist in geometrical isomers, so B is present. Out of those geometrical isomers, cis was found to be optically active. Previously we have seen dichelated complex with two monodentate ligands can be optically active in its cis form. So it can also have optical isomers. So enantiomers are also present. Sulfate is present, chlorine is present. They can exchange between the coordination and ionization sphere. Sulfate can enter in, chlorine can come out. So ionization isomers are also present. Linkage isomerism, there should be an ambidentate ligand. You don't find any ambidentate ligand. So first option with 3. Go for the second option. 4 amines, NO2 taken twice. It is just like, if you could remember, in the last class we have discussed MA4B2. MA4B2. MA4B2 will have 2 isomers. One is cis, another one is trans. All these are monodentate. There is no chelating ligand. Since there is no chelating ligand, no enantiomers. There is no enantiomer for it. So A option is not there. But geometrical isomers are present. Next, ionization isomerism is possible. NO3 can exchange for NO2. So ionization isomerism is also possible. Linkage isomerism, yes or no? Yes. Nitrito N, nitrito O. Suppose if it is linking to metal with nitrogen, or it may link with oxygen, you call it as nitrito N, nitrito O. Or you may call it as nitro and nitrito. That is the older version. Newer version is simply you call it as nitrito N, nitrito O. Okay? So it also has a linkage isomer. Come for the third one. COEN, PN, NO2 taken twice, Cl. NO2 is present, Cl is present, ionization isomerism is present. NO2 is present, linkage isomerism is also present. So we have C as well as D. Next thing we have to see is whether enantiomers and geometrical isomers are present or not. Yes, what is PN? not pentamine. Propylene diamine. En, Pn, Tn, all these ligands I have given you. I am just drawing it here. Suppose I take this as En. This is Pn. For your convenience, I am putting it like this: NH2, CH2, CH2, NH2. This one, there is a CH3 here. Pn and Tn are structural isomers to one another. Okay? So that will give you another type of isomerism. What is that isomerism? Ligand isomerism. If at all Pn and Tn exist, they can give you ligand isomerism. We have discussed it. But in this case, there is a En and there is a Pn. So along with En and Pn, you also have two nitro or nitrito. Right. So do you have any enantiomers? Definitely yes. There are two chelating rings. Let it be NO2 or let it be ONO. Let it be NO2 or ONO, but definitely enantiomer will exist. So A is also possible. And finally, geometrical isomers. Geometrical isomers you can very easily see. This is a cis, trans is also possible. But for the same, I am also drawing one more structure. These two are the same or different? They are different. They are different. Okay. So whenever Pn is present, you have to be careful. If at all it is Tn, trimethylene diamine, it is fine. But if at all it is Pn, can you see? This methyl is towards this nitrogen, whereas that methyl is towards below nitrogen. So there is a difference between these two also. Whenever you get Pn, just be little more careful. Okay. So you also have geometrical isomers. Cis is present, trans is present. Within cis again there are some variations, right? You can just note down that structure. This is one structure. You can write with ONO. Plenty of combinations will come for this isomer, remember. So this is a very important example. Either you can put NO2, 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 ONO, 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 NO2. 4 different combinations will come because these two are not ethylene diamines. One is ethylene diamine, one is propylene diamine. Okay, both are different. Suppose if I take trimethylene diamine, if I take trimethylene diamine, these two will be only one. If I take trimethylene diamine, just I am drawing that structure. Suppose if it is Tn, instead of Pn, if Tn is present, instead of Pn, if I am putting a Tn, then this is how the structure will be. So these two are different because of that methyl, Pn. But if Tn is present, you will have only such isomer. In that combinations will be there. It could be nitrogen, 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 oxygen, oxygen, nitrogen, and all other combinations. Okay. So what type of ligand they are asking? Watch it carefully. After a very long period, a notification has come. So we don't know what type of questions will be asked, whether it will be average or whether it is tougher. And if it is tougher, definitely you should have some edge over your other friends who are not coming here, so you definitely should have an edge. Right. Take another question. This is a simpler one. 1 gram of, fourth one, okay, triglycinato. This we have done previously, glycinato. This is triglycinato. This is called as facial form. This is meridional form. Okay. This is facial or FAC isomer. This is meridional. So what are FAC and MER? Cis and trans are geometrical isomers. FAC and MER are also geometrical isomers. Facial and meridional are geometrical isomers. Just as cis and trans are geometrical isomers for square plane complexes, for octahedral complexes you have cis and trans where 2 ligands are different from the other 4, and if 3 ligands are dissimilar, then you have facial as well as meridional also along with cis and trans. So do you have geometrical isomers? Yes, geometrical isomers are present. This can exist as its mirror image. So enantiomers are also present. Enantiomers also there. Next, ionization isomerism, there is no ion. Linkage isomerism, no, there is no linkage isomerism, because what we have glycinato is not an ambidentate ligand. It is a polydentate acyclic ligand. It is not an ambidentate, it is a polydentate acyclic ligand. Okay, coming to the next question. 1 gram of chromium H2O taken 5 Cl outside Cl2 dot H2O was passed through a cation exchanger to produce HCl. Next, the liberated acid was diluted. The liberated acid was diluted to 1 liter. The liberated acid was diluted to 1 liter. What is the molarity? What is the molarity of acid solution? What is the molarity of acid solution? You can take down the molecular weight of the complex. Molecular weight of the complex is 266.5. 266.5. So what is the answer? You just try to work out if you have a calculator. Just take about a minute of time, not more than a minute. Answer? I will give you a hint. To find out molarity, what is the formula? Weight by gram molecular weight into 1000 by volume. The volume they are making it up to 1 liter. They are making it up to 1 liter. So how should I find out the HCl concentration? Simply, if I can find out what is the concentration of my complex. First, let us find out the concentration of our complex. What is the concentration of our complex? Weight by gram molecular weight into 1000 by 1000, because it is being prepared for 1 liter. So 1 by 266.5. How much did you get? Just can you calculate? How much? It is almost 0.2 Not 3. Not 3. 0 0. After that. Okay. Now this is the concentration of your complex. That is the concentration of your complex. But 1 mole of this complex gives you how many chlorines which are what do you call labile? 2 chlorines which are labile. So if I am putting this complex into a cation exchanger, that will exchange the ions. So which ion gets exchanged? Chloride will get exchanged. Which chloride? That chloride which is present outside, which is present only in the ionization sphere. So if I am choosing 1 mole of my complex, how many moles of chloride can be liberated? 2 moles can be liberated. So if my molarity is 0.0037, what will be the molarity of your HCl? Double. So this into 2 will be the molarity of your HCl. How much will it be? 0, maybe about 7.5. So that is your answer. First of all, you are working out the molarity of your complex. Later on, 1 mole of your complex is giving you how many moles of chloride. Based on that, you simply multiply. Suppose there are 3 chlorides outside, whatever you get into 3. You have 1 chloride outside, whatever you get into 1. Okay? Write down the next question. The type of isomerism, the types of isomerisms exhibited by COEN taken twice, H2O, Cl2 and Br. It was from the previous question. Previously we have done that question where sulfuric acid treatment and silver nitrate treatment was done. Now the question is not how many isomers, but how many types of isomers can be seen for this complex. How many types of isomers? How many types? Okay, I should not take it into the brackets, but it is not in bracket, it is not a coordination sphere, some things are outside also. Just try to remember the isomerisms that we have discussed. Okay? Altogether, constitutional isomers we have discussed 9 types. Out of those 9 types, polymerization isomerism is not a true isomerism. Electronic isomerism, that is also not like a true isomerism. Conformational isomerism, it is also not a true isomerism, because atom to atom linkage was same in that. Atom to atom linkage, if it changes, metal to atom linkage changes, then I call it as a constitutional isomerism. But in polymerization isomerism, it is related to stoichiometry. Stoichiometry will be maintained, but complex will be changed. Conformational isomerism, complex is same, formula is same, but geometry will be changed. From square plane, it can move into tetrahedra. And finally, electronic isomerism, the complex is same, but a ligand called as a suspect ligand, nitrosyl, that will act as a different electron donor. Okay? So those 3 are not true constitutional isomerism. Along with that, you also have a ligand isomerism. Ligand isomerism, there is no direct change of metal to atom linkage. Metal to atom linkage is the same, but within the ligand there is a change, Pn and Tn. Pn and Tn, they bind with nitrogen only with the metal. There is no change in the atom to atom linkage, but within the ligand there is a change. In Pn and Tn, just now we have drawn previously, Pn and Tn are structural isomers to one another. So even that you can omit. Coming to the remaining isomers. What are the remaining isomers we have studied? Ionization. We have studied ionization. Hydrate isomerism. Hydrate is one form of ionization isomerism only, where water molecule will exist for the, will exchange for the ion which is present outside the coordination sphere. Then we have coordination isomerism. Coordination isomerism should need 2 different coordinate complexes, one existing as a cation, one existing as an anion. This is just only one complex, only one metal. Next, coordination position isomerism, for which a bridging ligand required and 2 metals must be needed, only one metal, no bridging ligand. So even this does not exist. Linkage isomerism. So how many we are left out with? Linkage, ionization and hydrate. Water molecule is present. Water molecule can easily exchange because ethylene diamine is a bidentate ligand. How many such ethylene diamides are present? 2. So it is giving you a coordination number of 4. 5, 6, 7, 8. It means there are 4 more ligands. I need just 2 more coordination numbers. So 2 will be present within the coordination sphere, 2 should be present outside. Which 2 will be present outside? That could be 2 chlorines, or that could be 1 bromine and 1 water, or it could be 1 chlorine and 1 water. It means hydrate isomerism is possible. Ionization isomerism is also possible with this. No linkage isomerism possible because there is no ambidentate ligand. Coming to stereoisomerism. In stereoisomerism, 2 chelating rings are present. So 2 chelating ring means anyway geometrical isomerism will exist cis and trans. 2 chelating rings for cis form you will be having optical isomers. So this is present, this is present, this is possible, this is also possible. How many types of isomerisms are possible? 4 types. But if you start writing the isomers, it will be more than that. You can write down the answer. 4 types. What are they? Ionization isomerism, hydrate isomerism, geometrical isomerism, and optical isomerism. Finished? Among the following compounds, next question. Among the following compounds, which complex has higher molar conductivity? Which complex has higher molar conductivity? Arrange them, continue the question, arrange them in their increasing order. Arrange them in their increasing order. See, for those who did not listen this isomerism, you might be getting confused. Don't bother, all these things will be there later. You can watch it later. You just try to attempt. These are the 4 different complexes. You just mention which is having the higher molar conductivity and arrange them in their increasing order. First, let us try to break them into ions. That will give you the answer, simple. If you can just break them into ions, that itself will give you the answer. I am breaking them into ions. K++, CO, NH3 taken twice, NO2 taken 4 times minus. Those are the ions. In the next case, there is no ion at all. This is neutral complex. In the next case, no ion. It is neutral. If I break them into ions, how many of these will come? Now just look. How many? 2, 5. Altogether how many ions? 5. So these are 3. These are 2 number. Okay. So just write down chromium 5 amine and nitro. Chromium 5 amine and nitro. Along with this 2 cobalt NO2 taken 6. What should be their charges? Now they should be in +3 oxidation state. If at all they are in +3 oxidation state, chromium there is only one NO2. So what should be the charge? What should be the charge? It should be 2+. So the same 2+ will also come here. Next, just look at this. CO NO2 taken 6 times. So what should be the oxidation state of cobalt? It should be 3. If it should be 3, how many negative charges are there? 6 negatives. Out of 6 negatives, if 3 are gone for the oxidation state, 3 must be going to the charges. So this should be 3 minus. Okay, and the last one, 1 complex chromium amine plus 3 chlorides. 3 negative charges. So complex will acquire 3 positive charge. So where you find more number of ions, molar conductivity will be high. This will have a higher molar conductivity. Okay, least second. Second is the least. Now you can arrange the order. What is the order? B is having least. Next is A, because it has only 2 ions. D is having 4. This is having 5. So BADC. How many charges are present for the first one? How many charges? 2 charges. How many charges? 3 into 2 plus 2 into 3. 12 charges are present. In this, 6 charges are present. In coordination chemistry, Werner's theory, I have given you a chart. In that chart, we have discussed how many ions are forming or how many particles are forming, how many charges, primary valency, secondary valency, all those things I have given in a single chart. That will help you. If you can just go through, that will help you. And most of them are previous exam questions. When I say previous exam, taken from different exams. You don't have JL every year. Okay, so you don't get those many number of questions. Okay, just write down a IUPAC name, because all this time you were working on isomerism. Just let us move from isomerism, we'll go to IUPAC. After that one IUPAC, again we'll enter into isomerism. Tetraamine, A-double-M, tetraamine diaqua cobalt 3, tetraamine diaqua cobalt 3, tetrafluorido borate 3, tetrafluorido borate 3, tetrafluorido borate 3. Write down its formula. First one, tetraamine diaqua cobalt. Cobalt is there. 4 amines. Tetraamine diaqua, 2 water molecules are there. Okay, there are 2 water molecules. Tetrafluorido borate, this should be the negative part because it is ending with 8, borate. So BF4. Now this is the anionic part, this is the cationic part, because they have given it as tetrafluorido borate. Okay, look at the oxidation states. Cobalt is present in +3, that is also present in +3. So altogether how many charges should come? Minimum 6 charges should come. But how many charges you have? Only 4. Only 4 negatives are there. These are neutral. Then how do you balance? It? Cobalt should get how much charge? +3. So let me take it as 3 plus. Are you getting my point? Cobalt should have +3. When do you get +3? These 2 ligands are neutral. So the complex should carry 3 plus charge. Okay. Next, boron should have +3. But how many are there? 4 negatives means 3 negatives are going for this. This should get minus. So this 1 minus you multiply, that will come here. This 3 you multiply with this. In coordination I told you, just crisscross. Whatever charge that is present, you just put it here. That will become the number of that ions. So whatever charge that you are expecting here, you put it here. Whatever charge you are expecting here, you put it here. So there is 1 of this cationic part, 3 of anionic parts. Now you check whether it is balancing or not. Altogether how many negatives are there? 4 3s 12. 12 negatives are there. So how many positives must be present? 12 positives. 12 positives, cobalt is in 3, 3 borons. Each boron is in 3. So 3 into 3, 9 plus 3, 12, balanced. So what is the formula? Here it is only 1, but here it is 3. So whenever a name has been given, you have to convert it into structure. What is the easiest way? Oxidation state is your hint. Based on the oxidation state, if the ligands are neutral, just calculate the charge present on the complex. Then you put it to the number of the corresponding ions. You just multiply it with the corresponding ions. You have to crisscross. So for the cation, what is the charge? Will go to the number of anions. For anion, what is the charge? It will go to the number of cations. Okay. For platinum example, I have discussed. Cobalt example also I have discussed in the regular class. And just a small reminder. This is a cationic part. This is a anionic part. This is like a complex. This is also like a complex. Though this is not a transition metal. So whatever is present within the coordination sphere should be written continuously without any space. And wherever you get ammonia, you have to write it as amine, not amine. A-M-I-N-E will come for ethylene diamine, triethylene tetramine and so on. But for ammonia, you have to put it as double M. And tetramine, don't remove one A, don't put it as tetramine. Tetramine means elision has been done. I said in the IUPAC nomenclature, no elisions. No elisions must be made. So no elisions must be made means if you get tetramine, write it as tetramine only, don't write it as tetramine. Okay. So put 2 A's. Tetramine diaqua. Olden days it was also called to be aquo. Now we are calling it as diaqua, cobalt 3. Without any space I have written it, and the oxidation state should be written in Roman numeral enclosed in parenthesis. Once that coordinate complex is completed, I am coming to the anion, give some space. After this space, then write down tetrafluoridoborate. Because this is anionic part, it should end with 8. Finally, continued with oxidation state. Again, within this there should not be any space, it should be continuous. Got it? Just a repetition of your IUPAC rule. Now let us move for isomerism questions. Now I will not be solving, just you give me the answers, because till this point I am solving. Write down the question. The number of geometrical, okay, this we have done I think just now, the number of geometrical isomers. But anyway, the number of geometrical isomers possible, the number of geometrical isomers possible for write down the question, cobalt En Pn NO2 taken twice plus number of geometrical isomers possible. What is your option? How many? Are you saying 2 or are you saying second option? Now you are confused. Just try to put it on paper, you will come to know what are the different geometrical isomers. There are 2 chelating rings. There are 2 chelating rings. How many? 4. The question is only about geometrical isomers. So you should not include any linkage isomers and so on. Only geometrical isomers must be mentioned. Though there is NO2, with NO2 you will get again NO2, ONO and so on. Those things should not be included. I just want geometrical isomers. So for that geometrical isomers, I have 2 chelating rings, I have 2 monodentate ligands. There are only 2 possibilities for it. What are those 2 possibilities? Cis and trans. But in the cis, I am not including any linkage isomerism, but here is a PN. Here is a PN. That PN can exchange. So once PN can exchange, now what is your option? Option? You are getting 4? 3. Answer is 3. Option is B. Okay. Previously we have done. Just please be careful here because these are previous exam questions. Some of them have been taken from GATE. This is one isomer. What is the second cis isomer? For that second cis isomer, this will be here. For the second cis isomer, it will be here. But put it as NO2 only. Linkage isomerism should not be included here. These two are cis geometrical isomers. Along with this, you also have a trans. In this trans, suppose if I am putting the ethylene diamine here, I am putting PN here. This is one isomer. Can I put it here and put the fourth isomer as you told? No, it is not possible. Here it is different because it is cis. Three-dimensionally, if you think, these two are different. But if I take this and if the fourth isomer, if I put it here, they are just one and the same. Okay? Hope you are getting my point. Fourth one, if I write it here, now look at 3 and 4. Are they identical or are they different? They are same, but these two are different. These two are different. They are same. So you don't put the fourth one. There are only three possibilities. Answer is B. If at all they also include linkage isomerism, then NO2 ONO will come. So they did not ask how many number of isomers. They have asked how many number of geometrical isomers. So please be very careful with the question. Okay. Write down the next question. The number of geometrical isomers for take down the complex CO glycinato taken twice, Cl taken twice plus options are 4, 5, 6 and 8. Without turning the papers, you just try to give me the answer. This we have done, but not directly as an example because I can hear the sound of the papers. This is like M, I am giving you the hint. M, glycinato, AB. If I put AA, capital letter or the uppercase, it is symmetric bidentate ligand, ethylene diamine. But I am putting A and B, capital letters or uppercase, it indicates a unsymmetric bidentate ligand. So 2-glycinato, this is C2. Even I can put AB taken twice. I can also put A2. A2 can also be put A small a or lowercase indicates monodentate ligand. But here we already written A, so you may get confused. For that reason, generally what we put is that alphabet which is not here. You can also put B2, you can also put A2, anything you can put. So for this we have done it. There we have put AB, AB, AB combination. Now instead of AB, directly you have to put your ligand. Okay, shall we put? Or else will you take some time? First what you do is put 2 chlorine cis, fix them. First let us fix chlorines. After fixing chlorines, here I am having glycinato. In that glycinato it is nitrogen to oxygen. So what I will do is nitrogen to nitrogen you take first one. Nitrogen to nitrogen, that is one way. Okay. Next fix chlorine, nitrogen to oxygen. Finished. Fix chlorine, oxygen to oxygen. 3 are different isomers. In the plane, 2 chlorines are present. Perpendicular to it are 2 nitrogens, nitrogen and oxygen 2 oxygens, I cannot take oxygen and nitrogen. If I take oxygen above, nitrogen below, it is just the same as this. Okay, so I got 1, 2 and 3. Any other combinations for cis? For cis, any other combination possible? No. So you got nitrogen to nitrogen, nitrogen to oxygen to oxygen for cis. Now let us write for trans. This is a previous exam question from GATE. I told you previous MSc entrances, Central University entrances, GATE entrances, all these questions will be taken, set exam questions will be taken, and they will also be asked for these notifications. I am taking NO. Any other combination you have for trans? For trans, do you have any other combination? Nitrogen to oxygen, nitrogen to oxygen, nitrogen to nitrogen, oxygen to oxygen. You don't have any other combination. But in cis you got 3, trans you got 2. Okay? Now what is your option? B, 5. Space is also perfectly matched. Even I cannot put another isomer, so 5 only. It is 5. Suppose if I am putting an extending question, how many of these are optically active? How many of these 5 geometrical isomers are optically active? First let us come for the trans. Suppose that if I pass a plane, this plane is absent, but chlorine to chlorine there is a trans pair. Once there is a trans pair, it will be inactive. There is a trans pair, it will be inactive. Pass an XY plane, that XY plane will pass through the 2 chelating ligands. 2 chelating ligands, XY plane will pass, chlorine to chlorine will reflect into one another, it will become optically inactive. So both trans forms are optically inactive. Cis forms, optically active. So how many are optically active? 3. How many optical isomers are present? 6. How many optical isomer pairs? 3. How many stereoisomers? 1, 2, 3, 4, 5 geometrical isomers plus 3. 8. Altogether 8 stereoisomers. 3 optical isomer pairs, 6 optical isomers, 5 geometrical isomers. Don't get bored. Today we have to do all questions, so that in the next class freshly we will go with other theories. Werner theory and isomerism we have completed. In the next class we will go for the next theories. Okay, write down the question. Determine the chirality label. This is for your confidence levels, checking your confidence levels. Determine the chirality label for cis COEN taken twice Cl2 plus. Determine the chirality label for complex I have given you. What is the chirality label for this? Chirality label means rotation. Rotation. For chirality labels we have delta and lambda. Delta is right rotatory or plus, this is left. Is it lambda? You are fixed. How are you saying lambda? Rotating anti-clock. But you are forgetting one thing. In your organic chemistry, just like RS nomenclature, where do you put the hydrogen? Generally you take it away. If it is towards you, you reverse it. Okay, anyway. What is the procedure? Rotate it so that one chelating ring is away from you. So I am rotating by 180 degree. Once I rotate by 180 degree, where do the chelating ring go? This chelating ring will go away from you. This chelating ring is going away from you. Now this is towards your top left, this will come towards your right. Okay. This chlorine is below only. 180-degree rotation, this chlorine will come here. 180-degree rotation, right? 180-degree rotation, 180-degree rotation. So this is what you are getting. Then what you have to do? Convert it into two triangles. This is the away triangle. For this away triangle, nitrogen, nitrogen and chlorine. This is the chelating ring. Now look at the front triangle, 1, 2 and 3. Just try to rotate so that this chelating ring will be parallel to the back. So once I rotate it, now this is the front triangle. To get this configuration again, should I rotate the front triangle to right or left? Right. So if I rotate to right, what isomer is it? It is a delta isomer, not lambda. Okay. So whenever a configuration has been given, just follow the procedure. What is the procedure? First rotate the molecule in such a way that one of the chelating rings is away from you. It is just away from you, it is in XY plane. So once you fix it, then what you do is convert them into two triangles. Back is one triangle, front one is another triangle. Try to rotate the front triangle to 60 degree. Why are you rotating? To make it parallel to the back chelating ring. So once it is parallel to the back chelating ring, to get this original configuration, should you rotate to clock or anti-clockwise? To get this clockwise. So I am rotating to clockwise, therefore I am calling it as a delta isomer. Okay? You can just note down. So don't always go by this logic. This logic I told you only for those examples. Starting from your side, as you move away, if you are drawing towards left hand side lambda, right hand side delta, that is fixed only for 2 or 3 examples. It is not applicable for all examples. So for that reason I tell you always the standard procedure. Whenever you are confused, go to the standard procedure. Finished? (180 and 60 degree rotation will bring you the triangles. Okay, next question. I will not do all these operations, just I will give you the structures, you try to get the notation. If you are able to do this, any question that they ask related to this configuration, 100% you will do the question in any exam. Just 3 more examples are there. Assign the configuration. Assign the configuration, whether it is delta or lambda. Assign the configurations for these 3. How good it will be if they give you 50-50 option? You have only delta and lambda. So if you say delta, I will say no. Then what is the answer? Okay, any answer for the A? A is lambda. Okay, I will not comment now, because I say no, then you will say delta. There are only 2 options. Okay, what you told is lambda, just let us check. Any other answers? delta. Only one more choice. Either it has to be lambda or delta. Okay, next one. Delta or lambda? Delta. Any other answer? Lambda? Okay. Third one? Third one? Delta or lambda? Fast, some say delta, some say lambda. Delta. Okay, some? So which one should I go with? First, what you told is right. This is lambda. This is not delta. And even for this, coincidentally, what you told is also right. First you said delta, that is right. This is not. How to imagine? Now at least are you able to imagine? Yes, it will take a few more days to reach. Chelating ring is towards your left hand side. This is your chelating ring. If you rotate by 90, that will be away. It is away. Now where is this ring? Above and away. So as that 90-degree rotation, it will come towards you. So once it is coming towards you, how will be the structure? This is the ring, 90-degree rotation. This is another ring, 90-degree rotation. So this is away. Now as you are drawing from towards you, it is like a clockwise. Can you see? If this triangle I am rotating parallel to this, I have to twist it towards my right hand side to get this. Therefore this is a delta. That is correct. In the previous example, it was a 180-degree rotation. It was little difficult. But in this case, it is just a 90-degree rotation. So once I am rotating it to 90, this is away, this will come towards you. Now you can see a triangle away, one triangle towards you. This triangle you rotate to 60, it will be parallel to this. To get the same configuration, rotate by 60 clockwise, you will be getting it. The same is the case with this. If that is delta, this has to be lambda. Okay, next. Is it delta or lambda? Lambda. Because everyone, what you told first was right. Now here, first or second? Second. Girls go with second. You are going with first. I go with. It is a trans isomer. It is a trans isomer. The same thing, if I just twist it, the same thing I am rotating. You just rotate, what do you get? Do you have planes? Plenty. XZ plane is present, YZ plane is present, XY plane is also present. All three planes are present. Therefore, this is inactive. So once it is inactive, neither can I assign delta nor can I assign lambda. So first one is lambda is right, last one is delta right, middle one you just write a point there. It is a trans isomer, hence it is optically inactive. Don't assign any configuration to it. Finished? Just 3 more questions we have. Number of isomers. I am asking you the number of isomers. I am not mentioning it like geometrical or optical. I am just asking number of isomers. For CO, En taken twice, ethylene diamine. CO, En taken twice, Cl2, bromine. Options are 2, 3, 4 and 6. 2, 3, 4 and 6. Answer? Just take a minute. Tell me the option. C. Any other answer? D. So between CD, not AB. B, you are going with B. And anyone with A? Will complete the options. Okay, A is not the answer. Between BCD, B is not the answer. Between CD, what is the answer? Right, there are two ethylene diamines. So what I will do is, I am taking cis, but whenever I am taking cis, there are two ethylene diamine rings, two chelating rings. So one of the chelating ring, if it is delta, the another chelating ring will be lambda. Okay, I need not draw the structures every time. So one is cis delta, one is cis lambda. What is this cis delta or lambda? CO, En taken twice, Cl2, Br. CO, En taken twice, Cl2, Br. One will be trans delta or lambda? No. How many isomers I got? 3 isomers. Now let me take cis delta again, but this time I am taking it as COEN twice, Cl2 Br. Can I include ionization isomerism into it? Because the question was related to only isomers. So include ionization isomer, put bromine inside and put chlorine outside. Again you have cis lambda. And then you have trans. So how many you got? D is your answer. You have 2 cis and 1 trans with 2 chlorines inside, and another one ionization isomerism. Again 2 cis and trans. I am not giving you the options, you just give me the answer. Rhodium C2O4 taken twice, oxalato, pyridine, NO2 2 minus. What are the number of isomers? Number of isomers. Number of isomers. How many? How many number of isomers? Two oxalato rings. Two oxalato rings. So you have cis and trans. How many cis? 2 oxalato means you will be having cis delta and cis lambda. Trans will also be there. But these 3 things, I am writing it as rhodium C2O4, I can write it as ox twice, pyridine, NO2. NO2, linkage. It is a linkage isomer, right? So rhodium, ox, taken twice, pyridine, ONO. These are the isomers. What is the oxidation state of rhodium? Not 6. This is your oxalato, bi-negative, 2 negative charges. So 2 such oxalato, 4 negative charges. This is 1, 5 negative charges. Out of 5 negative, 2 are gone for the complex, 3 should be present. So rhodium is present in +3 oxidation state. Okay, rhodium is in +3. Altogether you have 6 isomers. when we are working out questions, the time looks like very long. When we are taking the classes, it looks very short. Okay, this is very easy one. It was a GATE exam question. The number of possible geometrical isomers, geometrical, not the total number of isomers. The number of possible geometrical isomers for cobalt, oxalato, PMe3 taken twice, amine and chlorine. What are the number of geometrical isomers? Options are 2, 3, 4, 5. 2, 3, 4, 5. Answer? Oxalato is present, so first fix it. We have done similar such isomer. You can go through the previous pages. We have done similar such isomer by putting MAA so on. So here I am putting oxalato. There is only one chelating ring. Fix that chelating ring to some point. Then try to jumble the ligands. What are the ligands we have? First I am having P trimethylphosphine, two such ligands. So first put them trans, then put amine and chlorine. This is one combo. What is the another one? Oxalato is fixed. PMe3, put amine once. This is one. Fix oxalato. PMe3 is still here. PMe3 to PMe3. PMe3 to amine. PMe3 to chlorine. So here you put amine. Here you put PMe3. Even if I put PMe3 here, it is the same isomer. It is not like they are close. In space they are same. PMe3 is trans to chelating ligand. PMe3 is trans, not trans, sorry. It is just like cis to chelating ligand or perpendicular to chelating ligand. Perpendicular to it, perpendicular to it. Now let me take it parallel to it. Take PMe3 parallel, PMe3 parallel, then amine will come here, chlorine will come here. You do not have any other option. Altogether how many? 4. If you try to put chlorine above, amine below, it is just the same isomer, so you have altogether 4. Answer is C. Another GATE question, but it is so easy that even you don't need any options. CONH3 taken for Cl2 exist in two different colored complexes. You can just listen to the question. CONH3 taken for Cl twice exist in two different colored complexes. This is due to, why it is existing in two different colored complexes, which is due to linkage isomerism, coordination isomerism, geometrical isomerism, optical isomerism. Not coordination. For coordination you require two species. Geometrical. Linkage is not possible because you do not have any ambidentate ligand. Coordination is not possible because the complex is not a complex cation and complex anion. The other option, optical isomerism, is not possible because it is like Ma4B2. For Ma4B2 you have only two isomers, cis and trans for octahedra. For Ma3B3 you have two isomers, facial and meridional. So just remember these points. Ma4B2 only two isomers, cis and trans. Ma4B2. Ma3B3 only two isomers, geometrical, facial and meridional. Provided they are monodentate. If chelating ring comes, optical activity will also add. Write down another question. A square planar complex, iridium PPS3 taken thrice Cl, a square planar complex iridium PPS3 taken twice Cl, undergo oxidative addition with Cl2 chlorine, to give two products. These are linkage isomers, enantiomers, cis and trans isomers, FAC and MER isomers. Cis trans, sure? Don't jump into conclusions immediately. Just to take a while, because the same things will also proceed up to your exam. If it is fine, okay. Iridium PPS3 taken thrice Cl is a square plane complex, right? Iridium is a heavier metal. Since it is a heavier metal, it is very convenient in a square plane for coordination number 4. Either 4D or 5D, they mostly form square planar complexes. Even if the ligand is weaker, triphenyl phosphines are bulkier ligand, strong field ligand, you are getting a square plane. It is undergoing oxidative addition with chlorine. So whenever chlorine is coming and adding oxidatively, that chlorine, either it can add cis, or the other possibility is trans addition can happen. Suppose if it is adding this way, or it may add in another way. This is one chlorine. If another chlorine is coming from this side, this PPS3 is pushed. So two possibilities are there. Whenever Cl2 is coming and adding, there are two possibilities. One possibility is like Cl, Cl and Cl. How is it present? Meridional. In this case, it is forming a phase. So this is a FAC isomer, this is a MER isomer. It is just like Ml3X3 or Ma3B3. Just now I told you Ma3B3 will form FAC and MER. Ma4B2 will form cis and trans. Ma3B3 will form FAC and MER. So 3 triphenyl phosphines are present, 2 more chlorines are being added to the already existing chlorine. So 3 chlorines, 3 triphenyl phosphines is like Ma3B3, facial and meridional. What are facial and meridional? They are geometrical isomers. Okay. So anyway, geometrical isomer is not mentioned here. These two are geometrical isomers, and your option is D. Linkage is not possible. Enantiomer not possible. Now this is a tricky question, but options will give you the answer. Just if you carefully look at the options, you will get the answer. The isomerisms that are possible, for take the complex, the isomerisms possible for these two complexes. First option is optical and linkage. Geometrical and linkage. Optical and optical. Coordination and position. coordination and position. So which one is your option? Which one? B. MA3B3, it is just like MA3B3 will not have optical isomerism. Okay, we have established it. So this cannot be the option, this cannot be the option. For coordination isomerism, you should have complex cation as well as complex anion, but this is simply only one complex. You do not have complex cation and anion. So even this cannot be the option. What is your answer? So you are getting with elimination. This is geometrical. You also have NO2. Linkage isomerism is also possible in this, but only one option has been given, geometrical. For the second one, there is no geometrical possibility. Therefore, this has to be linkage. So linkage is this. This has linkage as well as geometrical, but only one option has been given, geometrical. So answer is this. It is a very simple question, but it might confuse a few students. Okay. We'll just take a last question. You might be exhausted with these questions, but even if one question comes, you will recollect my name for next 30 or 40 years, maybe 40 years if you are very young. Okay. This is easier only. The octahedral complex ion the octahedral complex ion which show both facial and meridional isomers, both facial and meridional isomers is, so which of these will show both facial as well as meridional? Without going through the previous classes, you just try to attempt this. It looks very difficult, but just after all these classes, all those examples we have done, this must look very easy for you. Trioxalato cobaltate 3, dichloro diglycinato cobalt, triglycinato cobalt, trisethylene diamine cobalt 3. Question: which of the below exhibit facial and meridional? Which one? B. Should we go with this? Facial and meridional. Ethylene diamine means it is a symmetrical bidentate ligand. It does not show facial and meridional, not possible, right, for ethylene diamine. Dichloro diglycinato, it is only diglycinato and dichloro. So dichloro means how many chelating rings? It can show cis and trans. This is diglycinato. But facial and meridional is not possible for it. Cis and trans are possible for it. For this, cis and trans are possible. Next, this one triglycinato, that can show. Triglycinato means we have done this already. N, this is facial, and this is meridional. So for triglycinato, facial and meridional exist. Trioxalato cobaltate, it is just like trisethylene diamine cobaltate. So it can exist as optical isomer, but not as facial and meridional. Okay. I think we'll close with this. We have some more questions, but it will take another half hour. Right. So we'll just close with this today. We have some more questions, but we'll be doing it in some other classes. Okay. So you just go through the coordination chemistry, whatever we have discussed till now, all the terminology, you just go through all the terminology. After the terminology, we have discussed about IUPAC nomenclature, go through all the rules of IUPAC nomenclature. Then we have started Werner's theory. Blumstein-Jorgensen theory was also there, but it was not of much importance. Werner's theory, questions will definitely appear from Werner's theory as to how many charges are there, how many ions are there, what is the chlorines, how many number of chlorines that have primary valency, or whether it has a dual valency and so on. Such a question can be asked. Werner has introduced the concept of isomerism. So we are studying all different types of isomerism, constitutional as well as stereoisomerism. In constitutional, we have seen 9 different types of isomerism. In stereoisomerism, we have seen 2 different types, geometrical and optical, right? So from the next class, I will be starting with some other theories, right?